Good morning and good afternoon, depending on where you are. Welcome to the technical seminar. This is for a CARB contract collection of agricultural equipment activity data. And before we get into the presentation, just a few housekeeping notice. The seminar is being recorded, and the recording will be posted on the project's webpage. And when you register, the meeting notice has the webpage URL link. And we're working on the final report. It's now going through the final formatting and remediation for accessibility. And we expect to post it on the project's webpage in a few days. And we will, in order to have a more streamlined process for the presentation, we will reserve the Q&A session after the presentation. And during the presentation, please keep your mics muted so that everyone can hear the presentation clearly. My name is Chao Zhan. I'm with the CARB's Research Division. I'm the contract manager for this project. And I will now introduce our speaker, Dr. Tom Durbin. Dr. Durbin is a research engineer in the Emissions from Advanced Vehicle and Fuels Research Group of CSIRT at UCR. He's an adjunct professor in the Chemical and Environmental Engineering Department of UCR, and he's a fellow of SAE International. He conducts research in the area of vehicle emissions with an emphasis on studying in-use emissions and activity, fuels, advanced technology vehicles, and particles. Before joining the vehicle emissions group, Dr. Durbin was involved in several other areas of research at CSIRT. Those include renewable energy and fuel sources and advanced vehicle technologies. So without further ado, I will turn the floor to Dr. Tom Durbin. Tom, I will stop sharing and you can share your screen for the presentation.
All right. Well, hello everyone, and I'm gonna go off video just so I can make sure there's no hang-ups with the actual presentation slides. So, but did want to introduce myself, and so let me just get the slide shared here in just a second, and we will start. All right, Tao, can you see the slides okay there?
Yes, I can see the slides, and this is in the editing mode. Okay, here we are in the full screen.
Yep, yep. All right. Well, want to thank everyone for attending. And so this was a study that we did under a CARB research contract called the Collection of Agriculture Equipment Activity Study. And I want to acknowledge my coworkers here at UC Riverside, including Chaz Frederickson, who is now working at CARB directly on PEMS testing and other things. And then I want to acknowledge at California State University at Fresno, Alex and Matthew, who were involved and coordinated a lot of the data collection in the field. So the analysis was more done on the UCR side, with the data collection predominantly being on the Cal State Fresno side. So first of all, to begin with, I think it's worthwhile acknowledging just the importance of agriculture in the California economy and just in a broader sense, If you look at it, it's one of the most critical most critical economic sectors in the state. And if you look at the estimates of sales and value, you can see that number is solidly in the billions, with some of these estimates depending on, how wide ranging you look at those economic impacts. If you look at primary jobs, secondary jobs, and again, you can see a wide ranging of estimates of the jobs, but in either case, it's fairly significant. When you look at the economy and the economic impacts of agriculture. So diesel engines are commonly used in agriculture applications, as probably everyone knows. If you look at the agriculture equipment in California, over 50% of that is in the San Joaquin Valley, which is a extreme ozone non-attainment area, serious non-attainment area for PM 2.5. So it's important to understand these impacts and the impacts they have on air quality, and to develop strategies to mitigate them that are as effective as possible. And if you look at the farm equipment impact in the San Joaquin Valley, you can see it's about 22% of the NOx. So definitely an area that is important in terms of understanding the emissions inventory and really making it accurate. So the importance of this accurate data for agriculture equipment is, in fact, that we need to improve and have very good emissions inventories. Obviously, that's what is utilized to develop and try out different strategies, both from a regulatory standpoint, but also from an incentives standpoint. And there's been a lot of incentive programs over the years for farm equipment. And one of the outcomes we've seen from our study is that there's been a lot of turnover of vehicles. And so it appears that some of those programs have been fairly effective. CARB, as part of its other programs, also is conducting basically surveys of agriculture equipment populations. They did so in 2008, in 2018, and they're working on another survey at this point as well. So there's a lot of tools they're using to improve the emissions inventories. And so, but an important link that you need with the population is that you also have to understand what the in-use activity patterns are, to understand how those patterns differ from other off-road equipment that might be more generically profiled. So the objective of this particular study was that we wanted to collect real-world data from agriculture equipment. And again, the goal would be to improve the emissions inventories, but also to inform different air quality and incentive programs that are ongoing in the ag area. And so we wanted to characterize agriculture engines in the San Joaquin Valley and to understand how they were operating under actual working conditions. So that was very important. And in terms of the measurements, we wanted to look at a lot of the engine control module, or ECM, parameters. We looked at fuel use, we looked at engine load, hours of use, engine speed, and torque were just a subset of the ones that we worked on for this particular study. So we had a variety of different funding sources for this project. The main funding was through the California Air Resources Board. but we had additional funding from the US EPA, from the San Joaquin Valley Air Pollution Control District, and the San Joaquin Valley-wide Air Pollution Study Agency as well. So just as part of a background to set a context for the work, we can look at some of the emissions inventory here. And here we are looking at the population of ag tractors statewide. And the reason we focused on tractors for this study is that they represent the vast majority of the agriculture equipment population. So we felt that was a good thing to focus on in terms of doing our measurements. So the top graph shows the populations, and here you can see the populations as a function of the tier of the engine. So tier 0 represents the older engines, and then on the other side, or toward the greenish colors, you're starting to get the later tier technologies, the tier 4 interim, and then the tier 4 final, which represent the vast majority of equipment going into the future here. So on the bottom, we can see the NOx inventory. And again, this is a statewide inventory for agriculture equipment. And what you can see here, the yellow line represents the newer inventory that was developed in 2021, that in part used some of this information, as well as some of the surveys and all the other things that they have been working on. And then you can see how it tracks with the old inventory. So you can see there's definitely a slight drop there. But again, all of that, it's important to continue to get that accurate. But you can also see, as a function of time, that this inventory is going down as well. And again, a lot of that has to do with the fact that you're getting rid of the older technology vehicles and bringing in cleaner and newer vehicles. And we'll see that even more as we continue through the slides today. Okay, so let's look at, just from a fundamental standpoint, kind of the things that you need to determine emissions inventory. So if you look at strictly emissions here, and this is emissions kind of more on a per unit basis here, it's a lot of determining the emissions as a load and an activity, which would be represented by a horsepower, an activity rate, and a load factor, and then emissions factors, which would be your emission rates. So here we're only focusing on the activity side of this. And so again, if you look at the grams per year, you look at the horsepower times the hours per year, times the load factor, and then basically you wind up calculating, taking all those factors into account to get your grams per year calculation. So here we're predominantly looking at the work, which would be the horsepower times the activity times the load factor. So the data collection was quite extensive for this program, and we actually wound up monitoring in one way or another over 200 pieces of equipment on 22 farms. And it's worth mentioning here that we had a lot of assistance from the ag stakeholders. They really facilitated us getting in touch with farm owners and operators that allowed us to deploy these units. We actually attempted to collect on even more tractors, but for a variety of reasons, we weren't able to necessarily complete all of the data logging and or monitoring. And so of that, a lot of this effort, about 127 tractors, we at least attempted to do with tractors. And so if we look at 185 of those, they were monitored for more than 10 months. So the idea was because uh, there's definitely a lot of annual variability in farming operations. We wanted to collect data over a year period. And so the vast majority of the data we had was collected over 10 months, and most of those were closer to 11 months. So that's the predominant part of the data set that we utilized here. We also have about 23 units that were less than 10 months. Again, that data still provides value in that even if we're not able to temporally profile the vehicles over a year, that activity is still real world activity that we could utilize. So of the data, we did data logging on 103 tractors where we actually installed data loggers. And if you look at the bottom, you can see a picture of a tractor with one of our staff there working on it. And then you can kind of see where the data logger plugs in to the ECM connection. And then there's a connector to the data logger itself, which is at the sort of bottom left corner of that second picture there. So that gives you an idea of what the data logger is and what it looks like. And so of these, the vast majority of these were actually collected on for over 10 months. And so it gave us what we think was a really valuable data set. We also looked at tractor data from rental agencies. In this particular time, one of the limitations was that we actually were doing some of this during COVID. So there were certain limitations with working with rental agencies and farms. And so we do have 35 records over 3 different distinct years of tractors, with about 12 of those being in harvest season. So we'll look at that data as we go on. Or one had 35 records, the other had 12 tractor records. So okay, so let's look at the breakdown here. We wanted to get a representative sample in terms of a number of dimensions here. So at the left, you can see this was our horsepower dimension. So we wanted to collect information from tractors representing a range of horsepowers so that as it was applied to the emissions inventory, it would be able to be utilized in a number of different categories. And then across the top, you can see that we wanted to have different types of crop operations. So we had sort of the tree farming, and then we had field and row crop farming. And below that, we had the older tractors, which we classify as tier 1, 2, and 3. And then newer tractors, which for this study we classified as tier 3 and tier 4. And again, a lot of that, the study dates back, 5 years or so. So we wanted to include both tier 3 and 4 because that was kind of what was in the fleet at that time. So of the equipment that was monitored, we had a total of 208 pieces of equipment. If you look at each column, there's a total and then a hem logged. So if you add up all of the totals there from the first column, you get 208. And basically what we did for those was engine hours. And then for 103 of those, we also basically collected the HIM data logging information. And you can see about 99, if you look at the total for tier 3, 4, for the tree, it was about 33, and then 66 for the field crops. So about 100 were in that newer technology regime. Okay, so looking at the farms by size, you can see here that the size in terms of acreage is in the left column here. And then the next column is the number of farms. And so you can see by number, we had most of our farms in the 250 to 10,000 acre range there. And then if you look at the number of tractors here, again, most of those fall in the 250 to 10,000 acre range. So on the left, we just want to give you an idea of the broader range of farm sizes here. And here, what you can see is that the red is the 2007 farms, and then the gray is the 2017 USDA ag census. So what you can see is that there was quite a bit of loss of these smaller farms. So in general, things are moving towards bigger farms, although we also emphasize small farms in our sampling as well. But just generically, that is the direction that the farm sizes are going over time. Okay, so we also wanted to consider the soil type, because there's a possibility that as implements go in, that the soil type can impact the activity if the soil is harder to plow through, for example. So what you can see here is this is an illustration of soil types on the right-hand side in terms of the percentage of clay, silt, and sand, which are sort of the main basically categories that are used for classifying soil. And over here on the left side, this is a pie chart of the tractors based on their predominant soil type. And so what you can see here is that over the 200 plus tractors, we had a good distribution of soil types, and most of the predominant soil types are represented in our sample. Okay, so let's look on to the information that we're acquiring, and then we'll go back. So we'll go back to this work function here as a function of horsepower and activity. So the horsepower comes from the population studies. Our goal was really to focus on activity. And so if you look at activity, our primary driver was to look at the annual hours that the tractors are operating. And what you can see here is that these green and blue dots represent the predominant activity for each of the specific tractors. So each of those tractors, each tractor is represented by a dot here. And what you can see here is that the predominant number of tractors here, or the predominant activity rather, is with these blue and green tractors, which are the tier 4s and the tier 3s. And this is a function of the engine age. And as you can see, as the age went out beyond, say, 20 to 30 years, it drops off to very low levels. And this was an important thing that we wanted to look at, because part of what we wanted to understand was what is happening with these older tractors. Are they still being used on the farms or not? And so that was an important question. So then we look at load factor here. And here load factor is basically the load relative to the maximum load of the engine. And this is a sort of the older distribution of load factors that was available in fact at the time we started, and we'll be able to compare sort of these numbers with what we got from the activity study as we go along. So 208 vehicles that we monitored for engine hours, 103 were monitored with data loggers, which is where we can get the load. Okay, so this is just a distribution of the tractors that we monitored on the study as a function of the age of the tractor. So again, a predominant number of the tractors were newer, but we also had a subset of tractors that we monitored that were older to understand how much these are actually operating. And at the bottom, the numbers in the parentheses represent the low or newest age and the lowest age. So if you look at the first bar, 84 tractors fell from an age of 3 to 8 years. And I believe that was characterized based on when we started to data log the tractor. Okay, so total activity that we monitored for this study. This is a function of basically the tier level and the horsepower level. And what you can see here is that it was quite a few hours. And here the blue bars represent the row crops, and the orange bars represent the tree crops. But as a whole, we were over 30,000 hours of data collection. So quite a bit here. And again, you can see that predominantly for the data logging, this was in the tier 3 and tier 4 categories, as you might assume, with a limited number of early adoptions for newer, older categories. Okay, so let's look at the distribution that I showed before and just show how that will be used in the emissions inventory. So again, we're showing predominantly green and blue dots are where most of the annual hours is. And you can see that in the past, the data set, there was a function of the inset basically is one of the graphs that was used in MFAC. And you can see that it's a bit steeper tail off than what was being used in the emissions inventory. So this data can be used to update that in terms of moving forward. Okay, this graph here just shows a box whisker with the hours annual number of hours on the left side of the axis, and then the different shaded box whisker graphs here represent the different tiers, which are shown at the top. So the on the left-hand side, we're starting from tier 0. Tier 1 would be the orange, tier 2 is the gray, tier 3 is the yellow, and tier 4 is the second lighter blue shade. And you can see here the data points in here, and the average is the line, or I think the average is the X, and I'm sorry, the average is the line, and I believe the X is the median. And then the box represents the 25th and 75th percentile of activity. So you can see that a lot of the activity for the tier 3 and tier 4 tractors winds up in this 1,000 to 500 hours of operation per year, with the averages ranging for those closer to 700 hours per year. Okay. So the next slide here, and most of the slides remaining here were from solely the data loggers, because when we looked at the engine hour meters, we weren't able to determine what day and how often those were used on a particular day. So we had to use data logger data for that. And so again, this is the familiar chart here, where the blue bars are the row crops, the orange bars are the tree crops, and then along the bottom, we have the distribution of tier 3 and tier 1, 2s. And then we have, going from left to right, lower to higher horsepower. And then the gray bar at the end shows the distribution for all of the data over all tiers and all horsepowers and all categories of farming operations. So what you can see here is that most of the activity is in the 3 to 6 hour range, with an average of about 4 hours per day. And again, do want to differentiate that this does not represent the operational day of the tractor. We are only monitoring when the tractor is actually on and operating. So if it's basically being loaded with an implement, or if it's stopping off for lunch, or being prepared to go out into the field, that would not be captured in this hours of use per day information that we're collecting here. And so again, along the y-axis is of course the average daily hours of use. Okay, so let's look at the rental agency data that we collected. And again, here we had 2 rental agencies. You can see the individual records in this, and of course you'll be able to see this in the slides that you download from the website. But you can see here that a lot of the rental days were on the order of 1 to 3 months of data that we collected. But when you look at the hours logged and the hours per month, but the one in the middle, the hours per day, again, we're also seeing numbers that are very close to the hours that we were getting from our data loggers, in that 4 hours per day range of, again, actually being operated with the engine on. And again, this one here, this particular rental agency, our second rental agency, here we had basically about a month and a half worth of data, but it was all during the harvest season. So when you account for just the high activity, you can see here that we had much higher rates of activity for that particular month relative to the annual average years that we were doing with the other data. Okay, so let's look at the engine load here. And so again, here we're again looking at data logger data with the row crops in the blue and the orange representing the tree crops. Average load is on the y-axis. And you can see here that there's a reasonable amount of consistency here across the different tiers and as well as the different horsepowers, as well as between the row and the tree crops here. And so if you look at the average, it represents about 28% as the load factor. But the range here was between 22 and 35. So a pretty narrow range there. And again, this load percentage is relative to the maximum load that the particular tractor basically based on its maximum horsepower rating. So each one of these was calculated individually for each tractor, and then we averaged together the loads to come up with the averages and the error bars here for this. Okay, so now we are looking at the fraction of operation on the y-axis as a function of the load percent in 5% load bins, going from 0 to 5 to 95 to 100% load on the right side. And what you can see here is that there is a lot of operation in this 0 to 10% range in terms of the percent load. And then as you get to higher loads, it steadily goes down as you get to the maximum load here. And again, we're looking at this in terms of these yearly averages. So that's what this represents, because again, we're looking at emissions inventories here. Okay, so daily fuel use here. Again, we've got daily fuel use in terms of gallons on the y-axis. And you can see here going from left to right, which is basically when we're going from lower, less than 50 horsepower, up to 300 to 650 horsepower. You can see there is a increase, as one might expect. Naturally, bigger tractors are going to use more fuel. If we look at the overall average over all horsepowers, which again can be a function of not only tractor size, but also how many hours those tractors were working each day, but we found an average of about 20 gallons per day. So a more universal metric that can be applied based on the number of hours, we wanted to look at the fuel use in terms of gallons per hour here. And so that is the scale on the y-axis. And then going from, again, left to right is increasing horsepower with a differentiation between the different tier levels and between the blue row and the orange tree crops. And what you can see is obviously that increasing trend from anywhere from about, say, 2 or less gallons per hour up to almost 8 gallons per hour for the bigger tractors. On average, you're looking at about 4 gallons per hour for the population as a whole. Okay, so idling data, we did see a bigger deviation here. So here the y-axis here is percent of daily idle, and then going across, we have the horsepower increasing, the different tier levels, and then the gray bar represents the overall average. And then on the far right side, we have idle percentages from the two main cycles being used for the certification of these agriculture and off-road engines. And what you can see is that, we generally are seeing idling percentages anywhere from 20 to 30%. Obviously, we have some outliers here or there. Some of those represent fairly small numbers of tractors, so we don't want to uh, overanalyze that data or overemphasize it, because if you look at the overall average with the gray bar, we're at about 27% on average, and you can see that the cycles relative to that overall average, we are definitely seeing less idle in the certification cycles in comparison with the cycles, with the actual in-use operational cycles. So DPF outlet temperature, we looked at this several different ways. So here the y-axis is the average DPF outlet temperature, and you can see that on an average basis, it was pretty close to 250 degrees C, which at that temperature, one would expect that the SCR would be operating on an average basis. But we're also going to look at other distributions. So here, DPF outlet was the predominant variable that was available on the vast majority of the tractors. So that's the one we tractored. But we're assuming that that DPF is going to be the inlet for an SCR system. So we also think that this is going to be a good measure of the exhaust temperatures that are going to basically govern how effectively the SCR is operating. So now you can look at a distribution. So we broke that down based on frequency percent on the y-axis, based on bends of temperature from 0 to 600 degrees. And I believe those are 20-degree bends in terms of the activity level. And then the orange represents the cumulative frequency as we go from lower to higher temperatures. And what you can see is that at around 200 degrees, which is about the time when the SCR begins to light off and the urea begins to be injected, we still have, we do have about 80% of the activity above that level, but we also correspondingly have about 20% of the activity that is below that level. So again, that's something that's an important consideration as you go through and look at developing after treatment control strategies and understanding how effective those will be when they are implemented in use. And of that 21%, about 17% was for loads below 10%. So again, we're seeing some of those lower loads and how they're impacting things as we go through the different variables. So number of engine starts. So here, this is the daily number of starts in terms of just simply number of starts on the y-axis. And then the x-axis, again, is lower to higher horsepower. And then the gray bar here at the far right shows that the average number of starts was about 3.5 per day. So if you look at one of those being a cold start, you are looking at a lot of those being hot starts. Now, some of those would be hot starts where the durations were under an hour, and then which would be about 2.2 average hot starts. And then there was a number of about 0.4 or 0.5, so one every other tractor was having an intermediate start, where the start was basically occurred after a soak of greater than 60 minutes, greater than an hour. So definitely the engine would be fairly cooled down at that point. Okay, now we are looking at three-dimensional plots of the torque percent for the tractor on basically the axis that is the y-axis for the 2D plot, and then the engine speed on kind of the x-axis for the two-dimensional plot, and then whoops, excuse me. And then the third dimension here is the activity percent. And so you can see from the colorations here that we have a lot of activity. If you look at the activity from bends relative to torque and speed, and I believe we pulled out, well, maybe not, or I think we may have pulled out idle here just to make sure that it's clearer to see. But you can see there is a decent chunk of activity when you look at the specific speed bends in this higher range, even though as an average, when you look at these lower and idle situations, it shows up a little bit less. And so the top left is the actual real world data over all of the tractors. To the right on the top side, that's the NRTC, and then on the bottom right, that's the C1 cycle. So you can see that there's a quite a bit broader distribution of horsepower and torque and engine speed relative to the certification cycle. Okay, so what we did with each of these data sets was we looked at the different snippets of time. And so this here represents the engine speed as a function of time over basically a 30-minute segment. And then so the top is the engine speed. The second one is the torque percentage. And then the third one is the torque percentage as a function of engine speed. So again, this is kind of more something we are looking at from providing background materials for test cycle development or evaluation. It's not, understanding torque percents as a function of engine speed percents gets into a lot of different complications. But these cycles, we believe, are representative or as close to being representative of the real world cycles as we can get them. And basically, this was every 30-minute segment was bend into a distribution of engine speed percentages and torque percentages, and then the snippet or the segment of operation that best represented the overall bend distribution, that was the one that was selected to be the representative cycle. So this represents the overall engine speed and torque profiles. We also developed speed and torque cycles or profiles for each of the different categories in terms of field and row crops and by the different horsepower categories. So 6 individual cycles were developed as part of this as well. Okay, so just to summarize, we looked at the hours of operation. When we looked and evaluated this data set, we were averaging about 4.1 hours per day, with a range in between, say, 3 and 6 hours. And if you look at the annual average hours of usage, it definitely showed a decline for the older tractors, with some of the newer tractors being up at 700 annual hours. Whereas if you look at the lower, older tractors, they're more in the 100 or so level. And then if we look at engine load, fairly consistent across the categories, with a average load of 28%, but with most of the variation, being between 22 and 33%. Idle fractions, again, most of it was within the 20 to 30% range, with an overall average of 27%. Fuel use, I think the most important metric is the 4 grams or 4 gallons per hour, with a range from about 8 gallons per hour for the heavier equipment down to about 2 gallons per hour for the smaller equipment. And so if you look at the end-use data collection, as you might expect, it covers a broader range of operation than the certification cycle. And but an important factor there is that it does include more low load operation. And so, and finally, we do have cycles that could be used for real world emissions, engine dynamometer cycles that were developed for each of the main categories. So based on this this study, with the 208 tractors, we think it does provide a very strong foundation for CARB and air quality agencies to basically improve emissions inventories and incentive programs. And we do feel that it would be important to consider these findings in different air quality programs, such as the Funding Agriculture Replacement Measures for Emissions Reductions, or FARMERC program, and also other incentive programs. But we also did see that some of those were valuable because there was a significant reduction in the amount of engine hours that we were seeing for those older tractors as they were replaced by the newer tractors. So we think it's also important to kind of look at more longitudinal or longer term assessments to continue to assess how things are changing in the in-use agriculture fleet, and to look at how these load distributions and idling times might change as the ag equipment fleet goes into the 2030 timeframe. Near term, we talked about CARB considering supplementing the results using a broader survey collecting information on the distribution of population, engine populations by tier and annual activity levels, just because we found such significant changes from tier to tier on this in this study. So finally, I want to acknowledge a lot of help from stakeholders in the agriculture industry, Roger Isom and Manuel Cunha from the Cotton Gin and Growers Association and the NYSE Farmers League, Chris McLaughlin and Kevin Abernathy as well. and then acknowledge our funding sources that I talked about in the beginning, from CARB, San Joaquin Valley Air Pollution Control District, US EPA, and the San Joaquin Valley Valley-wide Air Pollution Study Agency. And with that, I'm done with the main part of the presentation. So I'm going to go ahead and click this off so that I can see any questions and answer them and go back and forth between the slides. So Tao, I'll hand it back over to you.
Thanks, Tom, for the presentation. So we're now ready for the Q&A. We already have several questions in the chats. And just for everyone's information, we're not using the Q&A function in the Zoom. We're using the chat function that you can find in the sort of a banner below. There's a chat icon. Feel free to type your questions or comments. You can also use the raising hand function, and I believe that's part of the reactions icon, also in the lower panel. So I'm gonna read some of the questions in the chats, and then after addressing those, we can move on to maybe the hand raising questions. First one was from Michael Ross. The load factor reported on slide 11 don't correlate with the load factors on slide 19. Please comment.
Let's see here. Okay, so here we're looking at two different things. So this is the fraction of activity. I haven't gone through and actually done the calculation of what percentage are above and below the line here. But if I look at it, it's 2313. That puts us almost at 40%, and then another about 15%. So I think, looking at, just roughly calculating it, it looks like there's roughly 50% of the fraction below 50%. And, I'm assuming that the remaining 50% would be above that as well. So again, I haven't, just kind of glancing at it right now. That's kind of what I'm seeing. There might also be some deviations between things, whereas this might be based on overall averages and some of the other load factors, at least based on the different equipment types for the row and tree crops. Those might, the bars might represent different number of vehicles.
Thanks, Tom. Next track question, also from Michael Ross. Why were Tier 3 machines included in the DPF outlet temperature analysis, given that only Tier 4 would have SCR?
So here we were predominantly trying to look at, temperature in more predictive way, to understand if you had SCR going forward, what type of temperature would what type of temperatures would you be seeing that would be coming out of the DPF going into the SCR. So there, even though, the Tier 3s didn't necessarily have the SCR, we think that those exhaust temperatures would still be representative of engines running and that the DPF, whatever is coming out of the outlet would correspondingly be going into that next stage.
Thanks. Next question from Nicole Boofkamp. Sorry if I mispronounced the name. What is the estimated total tractor and other engine-powered farm equipment population in California?
I'm sorry, could you repeat that, Tao, real quick?
What is the estimated total tractor? So basically, what is the estimated? Sorry. My screen was moving a little bit. What is the population? Okay, I see that Sinju is already addressing this question.
Yeah, so some of the population estimates are in fact, a lot of that is done on the emissions inventory side.
Right.
So that, I know CARB takes this data and goes that next level.
This is Seungju from the other research division, and I found the other website, a webpage from the other ALB presenting the other approximate number of the other agricultural farm equipment, which is about 118,000 pieces of equipment statewide. And I included a web link for more information about that.
Thanks, Sinju. And I think as one of the earlier slides suggested, I think there's about 90,000 farm tractors, which is the vast majority of all the farm equipment that Sinju was referring here. Next question, also from Nicole. How can engine speed percentage go above 100%?
Yes, so engine speed here, when we do these comparisons, we're predominantly trying to understand this in the context of how one might apply this data to engine dynamometer testing. So here, the engine speed or the maximum speed for an engine dynamometer test is defined based more on the rated speed as opposed to the absolute maximum speed that the engine can attain before it basically lugs down. So that's why you see speeds that are above 100%.
Thanks, Tom.
And some of that is discussed a little bit more in the report when we get that posted.
Okay, thanks, Tom. Next question from David Peterson. Are DPF regeneration emissions incorporated into the emissions inventory? Transport and environment reported spikes of up to 1,000 times normal particulate emissions during such regenerations, according to independent laboratory tests they conducted. So the question is about DPF regeneration emissions, whether those are incorporated into the emissions inventory.
Yeah, so that would, obviously that would be on the CARB side.
This is Seungju Yoon from the other Air Resources, but again, I'm not in the emissions inventory, but we are working with our emissions inventory folks very closely, and I believe this question is about active regeneration. the other equipment with a DPF only. Yes, when the other active regeneration happens, a lot of particles can be emitted at the tailpipe. I believe our emissions inventory account for that. Tier 4 generation equipment comes with DPF and SCR. DPF mostly goes through passive regeneration, while the other engine load is elevated and temperature will increase and soot built on the other DPF will be burned, and then they are going to go through the other SCR as well. So we don't think there is a huge peak like what you mentioned, that the 1,000 times higher PM emissions during the regeneration. We don't see that high emissions, but the other our emissions inventory folks will account for that increased emissions if there is. So if you wanted to get more detailed information about this, then we can connect you with our emissions inventory folks. Please send us an email after this workshop.
Yeah, just one side thought on that, with the 1,000%, I guess the question would be, is that a mass or a number? And, secondarily, DPFs these days are largely at about ambient level. So, there's a couple things there that could impact that context. It might be 1,000%, but if that's the only time you're actually generating PM that's above ambient. So there's a couple of considerations there in interpreting that, I would say, as well.
Thanks, Andrew and Tom. I think we've gone through all the questions in the chat. I see one from Bill Robinson. Bill was asking, how well do you think the sampling scheme and resulting practicalities manage to span the smallest operations and more informal farming operations that may have more potential for older equipment than the large and/or corporate operations with resources to engage with regulators, researchers, and trade groups to participate?
Yeah, so a couple of thoughts there. One is, as we saw in one of the early slides, there is a decline, just showing slide 9, a decline in the basically the number of smaller farms that are operating. Secondarily, we did look at some of these parameters across different farm sizes as another variable. That, I believe, is in the appendix of the report. So we did some analysis there. There wasn't anything that really stuck out to us in terms of the variables like, hours of use or, or fuel use per hour, maybe some of the main things that one might consider. But definitely that's something to consider, and moving into that population study, basically to still continue to consider big versus small farming operations, I think is important, and really getting the feel for, are there still some of those old tractors on farms? We didn't see a great deal of that here, but again, we're still limited in that, we were representing just have the 22 farms that we looked at. You know, actually, maybe I'll ask Alex on that one if you happen to be online.
Hi, Tom. Hi, guys. Thank you, Tom. In relation to that, the team, including the CARB, make huge efforts to approach all farm sizes. One of the commodity groups that was collaborating with this project has smaller farmers as members, and they were extremely helpful. They provide us with a series of farm operations, small farm operations that they were willing to collaborate with us. We did the outreach and we had quite a few of them, including into our tractors. The question, the very small operations that they really have, it's less, the more informal farming operations, those people are a little bit difficult to find because typically they may not be members of a commodity group, and that limited our outreach efforts.
Thanks, Tom. Thanks, Alex.
And Alex is our collaborator from Cal State Fresno, just to put a name and a face together.
Yeah, thank you, Tom.
We have now gone through all the questions in the chat. Are there any additional questions from the audience? You can type it in or use the hand raising function. I'm not seeing any. So I think we've gone through all the questions from the participants, and I wanted to add that today's presentation slides and also the recording afterwards will be posted on the project's website, and I will actually include that link in the chat so everyone has it. But it's basically the same page that was referenced on the meeting registration link.
And Tao, I'll add one more thing. This work is also going to be published in the report, but there's also going to be a Transportation Research Board journal article that has been accepted for publication and is being published, and that will also be out shortly. So that's just another link of a summarized version of this that you can get.
Thanks, Tom. So I just sent the link to the project's webpage in the chat. Everyone should be able to see it. It looks like we don't have any additional comments or questions. I think we can adjourn the meeting. Thanks everyone for participating, and thanks Tom for the presentation.
Thanks.